Welcome to The Explainer. Today, we're diving into one of the most iconic laboratory experiments in all of fundamental chemistry, the dazzling chemistry of burning metal. We're going to walk through the exact steps, the crucial safety protocols, and the absolutely fascinating chemical transformation that takes place when you light metal on fire. Let's get right into it.
So, what actually happens when you set solid metal on fire? We're so conditioned by everyday life to think of metal as this incredibly stable, heat-resistant stuff, right? I mean, we cook our food in metal pans over open flames precisely because they don't burn. Sure, they get super hot, and yeah, if you heat them enough in some massive industrial furnace, they'll eventually melt into a glowing liquid. But actually catching fire, burning like a piece of paper or a log of wood, that completely challenges our baseline assumptions about how metals react to heat. But, as you'll see today, certain metals behave very differently under just the right conditions.
Now, anytime a science textbook stops you in your tracks with a big, bold caution warning, you know you're about to handle something highly reactive. Our source material here doesn't just suggest being careful, it outright demands the teacher's assistance and specifically notes that you need suitable eyeglasses. We aren't just mixing water and salt here, folks. We're actively initiating a volatile chemical reaction. This warning? It's our first major clue that the energy release we're about to trigger is intense enough that we literally need a physical barrier between the experiment and our eyes. And notice the physical distance required here, too. Not only do you need eye protection, but the instructions double down on the danger, demanding you keep the burning magnesium as far away from your eyes as possible. So why this heavy emphasis on the eyes? Well, it's because of the sheer visual intensity of the reaction we're about to unleash. We're taking a simple strip of metal, a magnesium ribbon, and we're going to ignite it. By holding it as far away as our arms will physically allow, we're minimizing our exposure to an incredibly powerful output of light and energy. Safety in the lab is always about respecting the materials you're working with, for sure. All right, so here's the careful choreography required at the lab bench to make sure our chemical reaction is both successful and safe. First up, you clean a 3 to 4 centimeter strip of magnesium ribbon with sandpaper. This primes the metal's surface by removing any impurities. Second, because of that intense heat we just talked about, you secure it with tongs. Never, ever use your bare hands. Third, you introduce it to the flame of a spirit lamp or burner. And finally, you position a watch glass right underneath to catch the resulting ash. It's a precise, methodical sequence of physical events to get this whole thing started. Take a moment to look at how this setup bridges the gap between our raw materials and the resulting chemical transformation. On the right, you can see the tongs firmly holding that thin strip of magnesium ribbon directly into the invisible heat of the burner flame. And right beneath it, the watch glass rests safely on the table, already beginning to collect the powdery residue falling from the reaction. Having this setup just right ensures we can safely observe the entire process exactly as it unfolds. The moment that metal hits the exact right temperature, absolutely everything changes. The magnesium ribbon combusts with a brilliant, blindingly intense white light. This isn't your standard flickering orange or blue campfire flame. The sheer output of photonic energy from this burning metal is incredibly powerful. And honestly, this is exactly why those safety warnings from earlier were so adamant about wearing eyeglasses and keeping the reaction far away from your face. The heat is rapidly unlocking a dramatic reaction, turning potential energy into an absolutely spectacular visual display. So as that dazzling light finally fades, we're left with a really stark contrast. Before the reaction, we had this solid, tangible piece of metallic magnesium ribbon, something you literally had to scrub with sandpaper. But after the flame dies down, that metal is completely gone. In its place, collected right there in the watch glass, is a simple white powder, just a pile of ash. I mean, think about that for a second. How does a hard, structural solid become a crumbling, powdery ash simply by being exposed to a flame? It didn't just melt into liquid metal, it fundamentally changed its physical state and its entire identity. Well, the secret behind this transformation all comes down to invisible chemistry. That white powder left in the watch glass actually has a very specific name, magnesium oxide. You see, the magnesium didn't just burn away into nothingness. Instead, the extreme heat from the burner forced the solid metal to bond with something completely invisible to our naked eye, the oxygen present in the air around us. The flame basically provided the energy required to make the solid metal and the invisible gas combine on a molecular level. And the result of that marriage between magnesium and oxygen? It's the brand new substance we see as that white powder. So let's summarize this definitive chain reaction. First, the heat acts as a catalyst. It's like an energy key that unlocks the metal's reactivity. Second, the magnesium reacts with the oxygen in the air. This is crucial because it makes the air an active participant in this experiment, not just empty space around it. And third, through that dazzling white flame, the two distinct elements merge to synthesize a totally new compound, magnesium oxide. It is just a perfect, elegant demonstration of chemical synthesis.
But this realization expands way past the laboratory bench. We just saw proof that the invisible air we walk through every single day contains oxygen powerful enough to chemically shatter a solid piece of metal and turn it into a pile of ash just by adding some heat. So if oxygen can do that to solid metal, what other unseen chemical dances are happening in the air around you right now? Maybe with every breath you take or every time sunlight hits a surface in your room. It's wild to think about. The world is incredibly dynamic, and chemistry is happening everywhere, all the time, even when we can't see it. Anyway, thank you so much for joining me for this explainer. Keep observing, keep questioning, and I'll catch you on the next one.